All right. Hey, everybody. Hope you're all here to learn about networking, because that's what I'm going to be talking about for the next 30 minutes or so. So, today, we're going to be discussing game networking, specifically establishing a connection between two peers across the public internet. We'll briefly talk about different kinds of common game networking architectures, and then get into technical aspects of the challenges imposed by modern networking hardware that make it actually difficult to establish a connection between two arbitrary computers on the internet. We'll talk about how to discover the restrictions of whatever network our program happens to be running in, and we'll discuss strategies to overcome those challenges, as well as strategies to roll with whatever challenges we get for stuff we can't solve. Finally, I'll hand over a bunch of free tools that I've been using in the hopes that it'll help you guys out. But first, who am I, and why do you care to listen to me talk about this? Hi, I'm Zach. I've been dabbling in game dev for like 20 years or so now. I've never actually released anything myself, but I've amassed quite a lot of knowledge on the subject. My day job puts me in a lot of network traffic tools, front-end, back-end, VPCs, Lambda services, like serverless architecture, stuff like that. I've also done a lot of network resolution for those as well. So, just jumping into a quick review on different kinds of game networking architectures. A lot of things that you'll see commonly is peer-to-peer, where all of your different players basically have a single host, and that host is just somebody else running the game on their computer. This is really nice because it's really cheap. You don't have to pay for the cost of any of these people running the games locally. You don't have to pay for any of the network traffic between them, but you may want to have something like a leaderboard or some kind of central repository where maybe your game characters are stored, something like that. If you think about a lot of modern AAA titles, a lot of those have dedicated central servers where everybody's connecting to a specific server hosted and paid for by, Blizzard or Activision or whoever has the money to host that kind of server. Certainly not us in this room. And then you have mesh networks, which are peer-to-peer networks where everybody connects to everybody else, or at least a large number of other players. A really good example of this is the first Dark Souls game. A lot of the soapstone messaging, that was actually done through a mesh network, and connecting through that, if you guys got the game at release on PC, was kind of a nightmare. It just didn't work a lot of times because mesh networking is incredibly hard to get right. So we're going to focus on peer-to-peer because as indies, that's about all we can afford most of the time. Dedicated central servers cost a lot of money, and mesh networks, you've got to do everything perfectly or it's just going to be absolute chaos. So when it comes to game networking, there's an endless supply of topics. You have optimization, different kinds of quantization methods. You have to worry about endianness of your packets, maximum transmission units of networking hardware along the way, packet loss, lag compensation, server reconciliation, rollback. The list goes on and on and on, but all of that supposes that you can make a connection between your two players in the first place. So, before we can even get to talking about any of those other subjects, we have to actually make a connection and start getting packets to flow. So, let's dive on in. So, when we have two computers on the internet, we know their IP addresses. If you go to IP Chicken or What's My IP, you can just send messages between our two people and everything's great. That's how the internet works, yeah? No, not since 1994. There's a lot of challenges that we'll discuss. The first one is that devices are rarely ever connected just directly to the internet. You're often behind one or more NAT devices like routers, modem router combo units like mine up there. And with increasing frequency lately, carrier-grade NAT devices, like those that filter requests for your cell phone. And just about every single one of those devices, including your actual computer, is going to have some kind of firewall of some description in front of it. And that's a good thing. That's generally appreciated that your home network discards packets that you didn't actually ask for. So, if you were on the internet circa 2002, we used to do port forwarding all the time. So we just set port forwards and we're still golden, right? It's kinda. The answer to that is yes, but also no. So as IPv4 addresses get more and more expensive, the answer shifts further and further toward no. Port forwards work so long as your ISP doesn't decide that it's cheaper to lease out fewer addresses and put a NAT up that you don't control between you and the public internet to make those addresses that they did pay for stretch further. So what the hell do we do? Enter NAT hole punching. Anytime you send a packet out of your network will always expect an answer from the destination to come back through. This effectively opens a little hole in your firewalls so that when you request, google.com, you can get a response back from their servers. And if the stars are well enough aligned and the network devices between your players are nice enough, that little hole that you can open is consistent in a way that we can intentionally leverage to have another peer establish a connection. And then once the traffic starts, you're set. For the most part. So, let's start getting a little more technical here. A NAT device knows or allows many devices behind it to be addressable by a single endpoint. The way it knows who to send data back to is through its routing table. When your router sees a packet coming from you destined for the wide area network, it replaces the source with itself and stores a reference to the original source, you, in a table. That lets the router route the traffic back from the destination to you. And you can see that in our little diagram down here. We send a packet from ourselves toward the internet. Our router picks it up, replaces our address, our 192.168.1.101, with its own actual address and sends it off to the internet. And while doing that, it stores that port in a routing table so that it knows when a packet comes back for my address at my particular port, it knows it was actually me that requested that, so it knows to give it back to me. Not all NATs are the same. There's a bunch of different algorithms that NAT devices use to determine how that mapping for the routing table actually works. And there's a bunch of different vendors that make routers that have completely different ideas on what a routing table should actually look like. Some only consider the source address and the port. So if I send a request, whatever I'm using to communicate with, that's all it cares about. Some consider the destination address, and some consider the destination port too. If either of those happen, we're in big trouble. And there's a lot more that goes into it. There are different time to live for the entries that are in them. Some of them, are all NAT devices, under high enough load, will evict entries even for active connections. Some of them only evict the oldest entry, regardless of the last use time. Some of them will prioritize evicting entries that haven't been used in a while. And some of them will evict entries that haven't been used, even if the routing table isn't full. It'll just clean up after itself after just a couple of minutes. So we're going to take all of that and simplify it down to just 3 basic buckets. Open NAT, limited NAT, and closed NAT. And we'll go through examples of each of these and examine what they mean for establishing a peer-to-peer connection one at a time. So, closed NAT is basically like a shifting sands problem. If the NAT considers the destination address or the port when calculating the entry in the routing table, you're just not going to be able to ever host a game. It means that no one can know the port and sometimes even the actual IP address used by an outgoing message from a computer behind that NAT until they've already received a message and have a return address, which is not going to work very well if you have a firewall that's going to drop that packet if it didn't expect it. A great example of this is pretty much everything using a cell phone carrier network, LTE, 4G, 5G, those like Verizon 5G home Wi-Fi cards, everything like that. Whenever you make a request to a service, your phone very likely has a different IP address and port as a return address for every single different thing that you connect to. It makes it hard for you to be addressable on the internet. And all of that combined makes it impossible for you to host anything because no one knows how to reach you first, even if you're actively trying to listen. So we consider that a closed NAT. But can closed NAT folks still play? Yes, they can, but they have a lot more restrictions. First restriction, they can't host, period. There's no way around it. There's nothing they can do. You're not hosting. You can only connect to hosts that don't require a facilitator. So that's our open NAT folks that we'll talk about later. and their NATs have a much higher probability of sudden eviction from the routing table once you do actually get a connection established, meaning that connections lasting for more than 5 or 10 minutes may suffer from disconnections. It's one of the reasons you see mobile games not really having active connections that last very long or very long rounds, because they're going to get evicted, and there's a whole lot you have to do for that. But since they're not the hosts, you can actually attempt to quickly reconnect, and if you want to have longer lasting games, your game can support a quick reconnection as a common case if you want that kind of support. Excuse me. So, most home ISPs fall within the limited NAT range. You have a modem router combo or a collection of routers that you control on your side of the network, and any other NAT devices that you don't control are actually sane and nice, and they don't consider the destination address, they only consider the source when creating a routing table entry. Which means you can reliably predict where their firewall will open when they send a packet out. Meaning peers external to the network can thread the needle and slip a message in before the hole closes up, allowing for a stable connection. People with limited NAT can actually also be promoted to open NAT with some legwork on their end to have an even better experience. There are still restrictions, just like there are for open NAT folks, but it's a lot less restricted now. They can host, but closed NAT players cannot join them. They need an external facilitator to help them open the firewall at the right times, and our closed NAT people can't even work with a facilitator. It just doesn't work. But they can join any hosted game. So if other limited NAT players host, or if open NAT players host, they can join and everything works great. And the likelihood of their connections being evicted from the routing tables of the other NAT devices is lower than those with the closed NATs, but still not zero. You still need to be able to plan for sudden disconnections and reconnect as necessary in your game's architecture while you're building it. Then we have our actual heroes, who are the open NAT folks. People who have an open NAT don't need a facilitator to accept connections. Their network stack is simply wide open and waiting for connections. These are folks with ports forwarded and no CG NAT in front of them. Their PCs might be DMZ'd in their router, or they might have universal plug-and-play settings not disabled on their network, which we'll talk about in a little bit. In addition, they also need to be lucky and have an ISP that doesn't have a CG NAT in front of them, or maybe they're paying for business class internet where they're granted a static IP address by their ISP. Usually costs a lot of money, but there are a lot of people that will run servers for their friends, and they'll have a open NAT and they'll have a static IP address, and maybe everybody pitches in a couple bucks a month so that they can pay for it. Regardless of the reason, they're basically superstars when it comes to connections in peer-to-peer games. Do they have any restrictions? No. They can host any game. They don't even need an external facilitator. People can just join them. They can join any game they want, but if they're joining somebody that's hosting with a limited NAT, they do actually still need to use the facilitator. And then there's effectively zero chance of their connection being evicted from a NAT routing table, since it's likely configured as a firewall rule somewhere. So, earlier I mentioned that limited NAT folks can actually promote up to open NAT. There's a couple of different ways that we can do that. Some of them are automated things that we can try during the upcoming network discovery phase, and some of them are things we could just tell the user to try if they want to be better at hosting. The first one is you can check for universal plug-and-play on the primary gateway of the computer that you're connected to. It's pretty hit and miss. A lot of times this is disabled for security reasons. Generally, it's not advisable to have UPnP enabled on your router because malware can take advantage of that. It sucks, but you don't really want to be able to go from a limited NAT to an open NAT from any old process running on your computer most of the time. The second one is if you put your PC in your router's DMZ. No one really does this anymore. It's pretty much considered to be a bad idea in almost all circumstances. Don't encourage your users to do this, but they can if they know exactly what they're doing and what they're getting into. They can do that. And the third one is port forwarding. You can tell them to set up their router to add rules for a permanent routing table entry, and it's pretty good if and when it works. It doesn't always work, but if it works, great. People that had limited NATs can promote themselves to open NAT and be much better at hosting with some effort on their end. So, we're going to step down another level and get even more technical. So, network discovery. Before we can start working on getting any two peers connected, we need to figure out what camp each peer falls into, since it greatly impacts who can host and how other peers can connect to them once they're hosting. To do that, we'll perform a process called network discovery, where we will discover the attributes of the network that we're on. So, in comes Stun, Session Traversal Utilities for NAT. Stun servers are super tiny services that'll effectively just echo back your address and port as the service sees it when it receives a packet from you. These are unbelievably cheap to run since they perform basically no work, and as a result, there's a nice curated list of free ones here. We'll get back to that later when we talk more about some of the free services that I use. But this is constantly running, it's constantly curated, it runs, it's really easy to use. Also, Stun servers have to be publicly accessible or they just don't work. So there's no shortage of publicly facing Stun servers at any given time. It's a necessary part of ensuring peers can connect on the internet. And the diagram here is it's an echo service. So I send a message, doesn't matter what my NAT structure looks like, it's going to tell me what it saw on the other end. So the first stage of our network discovery is to use these Stun services to make sure that we have a predictable external communication address and port when packets leave our network stack. We need to pick 2 Stun servers, each with a different address and a different port, and send packets to them. And very importantly, those packets have to come from the same port on our user's machine. So basically you set up a client server and send out a single message to each one from the same socket. If the address and port on both of those responses don't match, we stop right here and we label our unlucky peer as a closed NAT player. And if it passes, then we know that they are at least a limited NAT player, and we move on to part 2. So we can see in the first diagram down here, we send 2 different requests to 2 different servers that have different addresses and different ports. And if both of these come back with the exact same response, great. We know that you're at least limited NAT. If any part of those responses is different, you're done. Close NAT. You can't host. But you can still play. So, discovery part 2, we need to check to see if we have an aggressive firewall or not. To determine if they're open NAT or stuck at limited NAT, we need to have some service send a packet. We need to have our computer send a packet to an external service and have that service send us a packet back from an address and a port that we're not expecting to receive a packet from. This is a really important step because some network configurations that would otherwise be open NAT will still keep track of which destinations packets have already been sent to and still block packets from sources that don't match a recently requested destination, even if the port is open on the routing table. So that's also very important. So if we get that unrequested packet, then we're open NAT. Great, awesome, hero. If we don't, then we're still pretty okay. We're limited NAT. We have our little diagram down here where we sent out a request to one server. That server told another server to send us a request. We get the request back. If we did, fantastic. If we don't get that second request back, if there's basically if it gets blocked by our firewall and more than just packet loss, we send a couple of those packets and make sure that at least one of them gets to us. If none of them get to us, then it's probably not just packet loss and we have a limited NAT. So once we have that, we move on to our rendezvous server. So our open NAT chads can host without any need for a rendezvous server. Everybody can just connect to them like they would any other publicly addressable thing on the internet. They need no special treatment, and things just work better for them. They also have good hair and teeth, and probably get free upgraded accommodations at hotels. Limited NAT folks, though, they need some help. Their network infrastructure is going to throw out packets that they didn't request first. So we need a way for them to request a packet from an incoming client before the client can connect, which honestly sounds like an insane chicken and egg problem when you say it out loud. Our host needs to know about our client before our client starts connecting. Right. So we have a secondary service that sits outside as a rendezvous to help us accomplish this. So we set up a service that our clients and our hosts know about that always exists. When a client wants to connect, instead of sending a direct connection request to the game host, they instead send a connection request to the rendezvous service, letting it know which host our player actually wants to connect to. Then our rendezvous service lets our limited NAT host send a barrage of packets toward the client and tell our client to send a barrage of connection requests to the host. With any luck, the host's firewall will open up and one of the client's connection requests will be accepted by the NAT stack, forwarded all the way through, get to the host, and start a handshake. And once the handshake starts, the packets start going back and forth, you got yourself a connection. It is an imperfect science. There's a whole laundry list of reasons this can fail. Packet loss, because we're sending packets on the internet. They get lost. Somebody's microwave can be on. The routers just, they don't like you. They don't like the way you look. They don't like the way you smell. Who knows? Both people can be on the same side of the NAT stack, and one or more of the devices may not allow connection hairpinning. Put that in as a question after here to figure out how I learned about that wonderful limitation. And some ISPs like blocking UDP traffic in general. That's just a thing that they do. They think that UDP means torrenting. So if you're using UDP packets, maybe you're just not going to be allowed to have connections go through for that player. And that just sucks. But all is not entirely lost. There is one final step here. If you can't get a direct connection, you can actually use a relay. It costs a lot of money and adds a noticeable amount of latency, but I figured I'd mention it anyways. Instead of connecting directly to your peer, you instead connect to a publicly accessible relay that stands between your peer and your host. All traffic is routed through the relay, so you never actually make a direct connection to your peer, but that also means you have to pay for all of the network traffic for your game through service fees, and it gets pretty pricey if your game uses a lot of bandwidth. If you're doing something like Discord, and it's just audio and you can compress the hell out of it, it should be maybe okay, but if you're doing a lot of real-time game stuff and you don't optimize it a lot, it'll cost you quite a bit of money very quickly. I'm not using relays because I don't have money for it. So, with all that, we now have enough knowledge to be able to make a connection between two peers. So first, we need to figure out if we're open, limited, or closed. Second, if we need a rendezvous, then now we know what it needs to do in order for players to connect. And before we open up for some questions, I'd like to tell you about some of the free resources and tools that you can use if you want to get even more technical. There's things that I'm using. These are the things that I'm using right now for my game, and I'm not a paid spokesperson or anything. These are just the things that I'm actually using. The first one is a free cloud SQL database, Supabase. Tons of integration helpers. They have a free hobby tier. The tier isn't a super strong machine. It's actually very, very tiny. But if all you're doing is setting up a rendezvous service between two players, it doesn't have to be very strong. 500 megabytes is not a lot of storage space, but it'll hold a fair number of game lobbies during your prototyping phase. And if your game ever goes big, you can throw a couple of bucks and make it a lot bigger. The next one is free cloud serverless functions through Vercel. It's oriented and really, really heavy pushing like front-end Next.js developers with its marketing, but in reality it's just a wrapper around AWS Lambdas that prefer to run JavaScript and TypeScript code. The really cool thing is that it attaches directly to a GitHub repository and has full CI/CD out of the box. You just push to master and your app updates. You can write a quick REST service really quickly, and it has direct connect buttons to integrate with Supabase with one-ish click. One really nice thing about using this service is that because it's serverless functions, technically the machine that forwards the HTTPS request for a REST API is not actually going to be the same machine that handles the request. So when you need to send an unrequested packet back towards a user during the network discovery phase, you're technically already on a machine that the requester doesn't know about. So you can just fire off a packet and it's going to be an unrequested packet. So you just kind of get that guarantee for free out of the box, which is great. The free tier has a ton of headroom in the prototyping phase and development, and even enough for a couple of rounds of full play tests per month with tons of room to spare. If you want to get even more technical, I have a couple of Godot guides for implementations on the network discovery phase as a written guide, so you can just stroll through it at your own speed. It actually goes through selecting stun servers, preparing stun binding requests, and sending those and reading the results back. It doesn't actually cover the creating the APIs in Vercel or the firewall checking on the rendezvous servers. That's kind of left up to an exercise to the reader. And I also have a Godot implementation for user authorization during pre-connect as a written guide. This one helps with letting you set passcodes on your lobbies and ensuring that only players that get the passcode correct can actually join the lobby successfully. So if you want, when we post the slides after this, you'll be able to just click on those links and read through those if you're interested. And that opens the floor up to questions. I went a little faster than I wanted to, but it's all right. Do we have any? Oh, actually, chat. Got a question from Sean. What indie/self games are you developing these days? So, I am developing a car combat game in Godot that is meant to be like 90s internet gameplay. So it's all TCP/IP connections. It's actually UDP, but kind of how it was in the 90s. You have like a really basic lobby browser, and you can just join games, deathmatch, team deathmatch, King of the Hill, Moving King, stuff like that. And I don't want it to be like this crazy match-make thing. Just you and your friends could shoot each other up in cars and go on with the rest of your day. Larry asks, how do we get the URL for those resources? I will post a link to the slides at the end of this so that everybody can see everything and go through it. Larry also asks, I want to hear the hairpin story. Yeah, so my network, the one in here, doesn't allow hairpinning. So if I have my Steam Deck behind me on hosting my game and my desktop wants to join, even with like NAT punch through and all that, I can't actually connect within my same house to myself because the network requests are coming from inside, and the network just, I don't know, freaks out and decides that it doesn't feel like making that connection. It's just one of those things. It's an imperfect science. Sometimes it fails, and it just blows up. Sean asks if the public stun servers have anything like an uptime guarantee. No, they don't. They actually do go up and down pretty frequently. There's usually about 200 or 300 of them in the manifest that are active at any given time. So if one of them isn't working, just throw it out after a couple of retries and pick a different one. You should have plenty to work with. They are checked every 2 hours, though. So there's basically the GitHub action that runs and curates the list does actually make a request to each of them and verifies that they're up and running every 2 hours, and it makes sure that they're still in that list. You mentioned the mesh network before, and it sounds like it's not really ideal, so why does it even exist in the first place? What are its strengths and weaknesses? Mesh network, if you do it correctly, is one of the most powerful networking options available to you. Imagine if everybody had the same authority level as a host, and one of your players that was the host, like the primary host, they lost connection. You don't have to do a reconciliation phase. They drop out and everybody else keeps going like nothing happened. You can offload, for instance, if a new player joins in, some players send some data, some players send other data. You can actually kind of handshake and figure out who's going to send what, so that you don't have one player that just sends everything as one big block to the new player. They just kind of get little pieces of it and catch up quickly. It's also really good for self-repairing networks. Like the internet itself is a mesh network, like the whole thing. So if you do it right, it's awesome, but it's incredibly hard to get it right. And that's why generally we don't do that, because it takes so much overhead effort to get that working. Did you explore any out-of-the-box network services prior to working from scratch yourself? Mirror, Photon, etc. No, I didn't. And I wanted to solve this problem myself because I wanted to understand more deeply how the network infrastructure actually works when you're making a game. That way, if I do go to Steam networking in the future and something goes wrong, I've got a pretty good idea of where it went wrong and why it went wrong, and like it'll inform my ability to fix those things later. If you're just diving straight in and using those tools right off the shelf and you don't have that foundational knowledge, it makes it a lot harder to debug it. It's not impossible. I'm not saying don't do it, but it doesn't work great for me. All right. Do we have any questions that I missed in here? All right. I think that covers it.
Awesome. Well, thank you so much for this presentation. This has been awesome. Really good to see and think about.
One of the last things that I want to leave everybody else off with, a lot of these slides are a lot wordier than generally what you see in slides, and the reason that I did that is because it's a lot of information, and I don't want you to have to go back and watch the video to understand what I was talking about. So you can just crack open the slides, and everything is there in conversational format, as though you could probably hear my voice while you're reading it and the inflections that I gave, and it helps kind of cement all that stuff in. But you don't have to watch the video again later to basically get everything back out of it. Two more things that popped up in chat. All right, I'm going to stop the recording now.